Okay, so for this problem from the 2024 Imosl N2, we're given this requirement for a set S that for every A, B, and S, there exists C and S with A divides B plus 2C, which is weird. And we want to determine all finite non-empty such sets of positive integers. Let's first guess the answer. Now, if S only has one element, A, then A equals B equals A gives C equals A, so that works. S can equal A. And then after fiddling around for a while, you'll see that A over 3 also works because if you take B equals C equals A over 3, it works. So next, you fiddle around for a while, and you can't seem to find another solution, so let's just put it there. Now, the next thing to notice is that if A is really large, for example, A is the largest element in S, then B plus 2C, it cannot be 3A. It can't be as large as 3A unless B equals A, and in which case C equals A just trivializes it. So let's say A is maximal such that A is an S. This exists since S is finite. Next, take B not equal to A. Now, B plus 2C will equal A or 2A. Now, in the first case, there's nothing special, but in the second case, you actually do not want the second case because then, for example, 2C will, the C will be A minus B over 2, which is quite close to A, and if you applied this again, you're leading yourself to the second case, most likely, which is also quite close to A, and you don't know what to do. Now, this is all psychological, but how do you prove that it can't be the second case? Well, it actually can be a second case, but then there's a sneaky way past that. If B is odd, it can't be the second case. Now assume B is even. Then if B is even, it might be the second case. But what if, for example, B is even and C is odd? Sorry, notation clash. D is odd. Then notice that if you take A to become B, B becomes D. Then this part is odd, but this part is even, so contradiction. So if B is even, then everything in this set must be even. Well, then a thought just comes up into my mind. Divide by 2. Now, we can keep dividing, and eventually they must be all odd, which means we've gotten rid of this or 2A part. Now, that also means that for all B in S, A minus B over 2 is an S. This is good since if B is too small, say, it will, so psychologically, it will point towards B over 3. It will converge towards B over 3, which, just kind of forces it not to be a positive integer. But we haven't found a way to say this formally. Now, how do we do that? Well, we keep applying this thing. So, if we keep applying, we'll end up with A plus B over 4. Then we'll end up with 3A minus B over 8. 5A plus B over 16. And pattern seeking will give you, let's only consider every other term because they all have a plus in front of B, which is convenient. It'll become 2 to the 2K minus 1 divided by 3 times a, and then plus b over 2 to the 2k. Now, this is an integer for every k. We're assuming that, which means multiplying by 2 to the 2k, we get 2 to the 2k minus 1 over 3, a plus b, is equivalent to 0 modulo 2 to the 2k. Now you immediately realize there's a 2 to the 2k here. Get rid of it. There's a negative 1 here. What do? Take it to the other side. So now it becomes, it's 3 inverse times a mod 2 to the 2k. Okay, now you don't see any k in here. Does that mean b is 1/3 of a? Technically, no, because 3 to negative 1 will change when k changes, but there's a simple way to get rid of that. Multiply by 3 on both sides, and 3b is equivalent to a for any k. Taking k large enough, we get 3b is equal to a, which means we are done, and this are the only two possible answers.